Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IAC. It's my pleasure to introduce today's speaker, Professor Pranay Sharma. He'll be speaking on reinforcement learning in non-stationary environments. He is an assistant professor at IIT Bombay in the Center for Machine Intelligence and Data Science, CMInDS. Till Jan 2025, he was a research scientist in the Department of Electrical and Computer Engineering at Carnegie Mellon University. He finished his PhD in electrical engineering and computer science at Syracuse University. Before that, he finished his BTech and Tech dual degree in electrical engineering from IIT Kanpur. His research interests include federated and collaborative learning, stochastic optimization, reinforcement learning, and differential privacy. Audience is encouraged to ask questions at any point during the talk. Questions may be asked either by unmuting and speaking directly or by typing them in the chat box. Over to you, Professor.
Okay, thanks a lot for the kind introduction, and thanks again for the invitation. It's always a privilege and honor to speak to an ISC audience. So sorry I couldn't be there in person, but I was in ISC just a few weeks back for the reinforcement learning workshop. So I see some familiar names in the audience. So hi, everyone. Okay, so I'll be talking about our recent work on reinforcement learning in non-stationary environments. And this is the paper you see at the bottom. Yeah, feel free to interrupt me at any point. So this paper got accepted in PMLR a few weeks ago. Okay, so yeah, this work was done in collaboration with these people. So Niharika is a fourth year PhD student at CMU EC. Ishika was a master's student in the same department when we did this work. Currently, she is a PhD student at UIUC. And Guana and Gauri are faculty members in the EC department at CMU. Gauri was also my postdoc advisor. So, as is evident from the title, this talk is going to be about reinforcement learning. And there are a number of applications of reinforcement learning going all the way from data centers, which are like the buzz for past few years since AI took over the world, all the way to self-driving cars or even stock market prediction or the many apps that we used, which have some kind of recommendation systems. And the canonical definition of reinforcement learning, which is sequential decision-making uncertainty, applies in all these applications. And as is the case with reinforcement learning applications, we want to do well in the long run, but in these applications specifically, we want to do well in a time-varying environment. So in data centers, depending on the climate conditions, their energy usage goes up and down. Depending on the current trends, their energy usage goes up and down. Similarly, in stock markets, depending on whether it's a bear market or a bull market, the stock market behaves very differently. And therefore, the investment strategies need to evolve. And similarly, again, in recommendation systems, depending on the time of the year, seasonality, different patterns of customer behavior, the kind of recommendations that are made to the users have to evolve. So once again, we want to do well in a time-varying environment and in the long run. But so far, all these terms are very hand-wavy. So I would concretize very shortly, what do we mean by doing well? What do we mean by a time-varying environment? And what do we mean by doing well in the long run? Okay. So this will be the outline of the talk. I will first begin with some background, which it would be very elementary for some people in the audience, but just for the sake of completeness. So reinforcement learning problems are usually modeled using Markov decision processes, and we would denote a Markov decision process in the following way here. So we have the set of states denoted by S, the set of actions denoted by A. In this work, both sets are going to be discrete, finite. Then at any point, the trajectory would be given by the following quantities. So the current state at time t is st. The action we take in this set is at. This action would result in some reward rt, and then we would transition to the next state st plus 1. Okay. And we have an agent which is interacting with the environment. So the agent takes some action depending on some probability distribution. Given a certain state, it has certain set of actions that it can take probabilistically, and these actions are taken using this distribution or policy pi. We have rewards, and the next state is given by this probability distribution, which depends on the current state and action pair. And we would use the following notations in going forward. So the transition probability matrices, which help us select the next state, will be denoted by capital P. The reward vector, the reward that we get when we take a certain action in a certain state, we can list all the possible values of it, and this gives us the reward vector. And when we are in a stationary environment, which doesn't change over time, in that case, both the transition probability matrix and the reward vector are time invariant. So in that case, we can denote it by P and R. In our non-stationary setting, these will be time varying, so they will have an additional subscript denoting the time. Okay. And usually in reinforcement learning, if you look at some of the like most of the literature in reinforcement learning, they usually work in the discounted reward setting, where we try to maximize the cumulative reward over a possibly infinite horizon, but we discount the future rewards compared to the current state. So this gamma is a constant which is smaller than 1, and we are discounting future rewards by gamma to the t. Here we assume that the initial state comes from a distribution eta, and all the actions are taken using policy pi. However, we would be interested in average reward. So I would talk about certain motivations for using average reward shortly, but just for the sake of definition, this is how we define average reward. So we look at the expected value of the total reward that we have accumulated, and we normalize it by the time horizon, and we take the limit to infinity. Okay. And under certain ergodicity assumptions, I would again come back to these later in the talk, but under ergodicity assumptions, we can write a very simple expression for this average reward. So given the state comes from some distribution, this d pi, and the actions are taken using our policy pi, the average reward is just the expected value of the reward that we get in a state action pair. Now, this distribution from which the states are sampled, this is the stationary distribution that is induced by policy in the environment P. Okay. So like given this definition of average reward, you can, under ergodicity assumptions, reduce to this expression. Okay. But why do we even care about average rewards? So the problem with discounting is that it introduces certain time preference. So somehow we prefer rewards now compared to rewards later. Okay, we discount the rewards that are going to come in the future, and sometimes that's not always a good idea. So this is a cartoon which appeared in the New Yorker magazine several years ago, and this shows someone in a suit and tie. The funny thing here is that the suit is torn, but he's still hanging on to it. And the person is saying that, yes, the planet got destroyed, but for a brief, beautiful moment in time, we created a lot of value for shareholders. So this was essentially prioritizing short-term reward excessively over what we do in the long term. And we don't want to do that. So average reward emphasizes steady state behavior. It doesn't prioritize short-term gains over what happens in the long term. And where does this make sense? So it's the right notion to use when the system is supposed to run forever. So some examples of that include queuing system, where we want to minimize the latency or maximize the throughput over a very large time horizon. Or it is relevant in communication networks or power grids, which are like entities which are expected to run forever, or it's also relevant in recommendation systems where we have continuous users. So based on the description so far, if you get this sense that average reward is the nobler thing to do, I should point out that a lot of these addictive apps like TikTok and Instagram, they actually work with continuous users. So they are prioritizing average reward in some of their algorithms as well. So this is not the noble thing to do, but sometimes it makes sense in the problems we are working. Okay, so and just like we have value functions in discounted reward setting, we can define relative value functions in the average reward setting. So I'll get to why this relative is coming in a second. But given a state S, we can define the relative state value function for this state in the following way. So we essentially sum over our entire reward function, but then we look at how different it is from the average reward. Okay. And similarly, we can define relative state action value function where we again sum over the rewards, but we compare it against the average reward. So given that you start in state S and begin by taking action A in state S, and then let the policy and environment take over, in that case, how well do we do compared to the average reward? Okay, so essentially we are quantifying how much better a certain state is or a certain state action pair is compared to the average reward. And just like we have Bellman equations for the state value and state action value function in the discounted setting, similarly, we have Bellman equations in this setting. So given a certain value of the state action pair, we can come up with the value of the state value function. And similarly, given a certain value of the state value functions, we can come up with the relative value functions for the state action pair. So the thing to notice here is that we are taking care of this average reward.
I have a question.
Yes.
So in QPy, why isn't there a normalization? Like why aren't we dividing by T?
So that's a good question. Essentially, this we are because we are looking at what is the incremental change compared to the average, right? So that takes care of this thing here. So this JPy is essentially the difference between what you see in the discounted setting versus what you are seeing here. So this is the extra term. So this is taking care of that thing.
Oh, okay. So
Okay.
JPy is average reward.
JPy is the
value
average reward.
function.
Yes. JPy is the average reward, averaged over. So let me go back a few slides.
Yes.
Yeah. So JPy is the average reward.
So why wouldn't QPy blow up? How do we know that doesn't happen?
Like you can show this thing. Like it doesn't blow up this difference. Yeah, like this is easy to show. Yeah.
Sure.
Thanks. Okay. So like let's very briefly go over a taxonomy of different kind of reinforcement learning methods that people look at, and then we will settle on a specific method. So broadly, you can look at value-based methods or policy-based methods. So given certain policy, you want to maximize whatever value function you get. So with value function based methods, we are evaluating the value function for a given policy, but it has certain limitations when you go to function approximation setting. And therefore, people in some cases prefer policy-based methods. One example of policy-based method, one very common example is something called policy gradient method, where we define certain performance measure on our policy parameter. So if we are interested in maximizing the average reward, then this J becomes the average reward. Theta is the policy parameter, and we sort of do gradient descent on our theta parameter using this J objective. So we use an estimate of the gradient of J at theta and do gradient ascent because we are trying to maximize this performance measure. There are certain advantages because sometimes you can introduce some amount of prior knowledge about the policy into the policy parameterization. We will see an example of that when we talk about our specific algorithm. Sometimes policies are easier to approximate. So in this talk, we will work in the domain of policy-based methods. In policy-based methods, broadly, you can have actor-only methods or you can have actor-critic methods. So we have a picture of an actor. I hope several people know who this is. So actor-only methods can be applied in several settings, but the limitation is that they often suffer from the high variance because they are using an estimate of the gradient. On the last slide, we saw an example of a policy gradient method. Actor-only methods use an estimate of that gradient, which can have a high variance. Actor-critic methods, so these are two famous movie critics. Actor-critic methods take care of that limitation. So in this class of methods, we have two entities working in parallel. So given the current policy of the actor, the critic tries to learn how good this policy is, or more specifically, it tries to estimate the value function for that policy. And once the critic gives you an estimate of the current policy, the actor can modify its policy using some information given by the critic's estimate. Okay, so that's the idea of actor-critic methods. So essentially, we are looking for a policy which would maximize the average reward. Critic-only or value function-based methods have certain limitations. That's why we are more interested in policy-based methods, in which actor-only methods, again, suffer from high variance. That's why we want actor and critic-based methods. And on top of that, there is a class of methods called natural actor-critic, which is somewhat better than simple actor-critic methods. It utilizes second-order information. So these natural actor-critic methods, the natural comes from the usage of natural gradients in these methods, and they have been shown to converge to global optimality. Rather than converging to simple stationary solutions, natural actor-critic methods can converge to a globally optimal solution under certain assumptions. Okay, so just to summarize once again, we are working in the infinite horizon setting. We want to maximize the average reward, and we are in a non-stationary environment. And the class of methods that we settled on is a natural actor-critic type method. Okay, so next, I will describe what a basic natural actor-critic method is, and then we'll go to the specific algorithm which we proposed. So yeah, if there are any questions, I can take them. Okay, so let's look at natural actor-critic methods, and our method is built very closely on top of this. So in natural actor-critic methods, we have actor update and a critic update. So this is what the actor update looks like. As I said, the natural of natural actor-critic comes from natural gradient method, which we will see right now. So our performance measure is the average reward for our current policy. Let us parameterize our policy pi with the parameter theta. So pi theta gives you the current policy, and we are trying to maximize the average reward for this policy. Okay. And this is what a natural gradient step looks like. We have the gradient for our performance measure J, but we also have a matrix. And this matrix in natural gradient methods is the Fisher information matrix. So we can use policy gradient method theorem to compute the gradient which we need. So essentially, ignoring the expectation for now, what we want is we want a direction, like we want to move in the direction which would give us a better policy. And how do we compute what is better? Using the state action value function. Okay, so grad log pi is going to be modified by the value of the state action value function. And the state and actions are going to come from the stationary distribution. The action comes from the policy. Okay. And this matrix F pi theta, as I said, this is the Fisher information matrix. So this is the outer product of grad log pi theta. And again, the state and actions come from the stationary distribution and the policy, respectively. And with softmax parameterization, I said that it's possible to introduce some information into the policy using some kind of parameterization. So in this case, we work with softmax parameterization. So given certain parameter theta, this is what the policy of choosing action A in state S looks like. And with this softmax parameterization, the actor update of natural gradient method simplifies to something like this. So a quick question, does this update in blue, does this remind anyone of something?
Multiplicative weights.
Yes, of course. Thanks, Shubhada. So this is multiplicative weights. So a side note, like I only knew of multiplicative weights in online learning setting, but I found a ACM survey paper from Sanjeev Arora's group a few months back, which like it's a survey on multiplicative weights, and it shows it has applications in very, very diverse fields, even like computational geometry, which I had never imagined. So I would encourage you to look at it. So yeah, this is exactly multiplicative weights. And the problem so far is that we don't have this q pi theta, which is the value function, the state action value function for our current policy pi. Okay. But we discussed that this is what critic comes in for, right? So let's look at the critic now. So critic estimates these state action value functions using TD learning, temporal difference learning. So given certain state action pair S comma A, this is how the Q function get updated. You look at what is your current reward, and you look at what the current estimate of the average reward is. And this is the difference of the state action value function after transition and before transition. So from state S, after taking action A, you transition to state S prime, and in S prime you take action A prime. Okay, so Q S prime A prime is the state action pair at the next time instant. And because we are using an estimate of the average reward value, which again we don't know, so we need an estimator for this as well. So we use an estimator, we compute an estimate of the average reward, again, using our current estimate and the current reward value that we get in our current state action pair. So putting all these things together, the actor update, the critic update, and the average reward update, we end up with this algorithm, which we call natural actor-critic. So we initialize with a uniform distribution over actions in every state. And we initialize with the value of 0 as the Q function in all state action pairs. And we initialize the average reward estimate with 0 as well. And then we unroll our trajectory. So given state action pair ST80, we observe the reward that the environment gives us, transition to the next state ST+1 using the environment T, and then take another action in this new state ST+1, which we call AT+1. Okay, so after this transition from time T to time T+1, we have certain quantities which we use to create an estimate for the average reward. We also compute the updated value of the Q function, and we modify our policy estimate. Okay, and this process we repeat over time. Okay, now the problem so far is that the actor wanted to modify its policy, for which it didn't know the value function. Therefore, we brought in the critic. But in this entire algorithm, we implicitly assume that the environment is stationary. That's what was assumed by the existing analysis as well. But what if the environment is changing over time? The rewards are changing over time, right? So that's where our work fits in. And next, I'll describe the modification of natural actor-critic, which we had to do to make it work in the non-stationary setting. So we call this algorithm very unimaginatively non-stationary natural actor-critic. So under stationary environments, as I described earlier, the critic estimates the value function qt of the current policy pi t. It's not the exact value function, but critic creates an estimate. And then the actor uses that to evolve or update its policy. However, if we assume that the critic step size or the rate at which critic changes is much larger than the actor step size, in that case, approximately for any policy, the critic can achieve a good enough estimate of the value function, right? So at any time instant, the critic is able to a reasonable extent, estimate the value function for whatever the actor's policy is, right? However, that was under stationary setting. Under non-stationary setting, we have a few more challenges. So let's talk about them. So we assume that the MDP is modeled rather than by a single MDP. Now we have a sequence of MDPs, which is changing over time to model the time-varying environment. So rather than what I pointed out in the beginning, rather than having fixed transition matrix P and reward vector R, now we have time-varying transition matrix T and reward vectors RT. And therefore, now actor is choosing a moving target. The actor is trying to find out the optimal policy at each time instant. So if we look at this expression a little closely, this is the average reward if the policy, the current policy pi runs and we are in a stationary environment. So if the state comes from the stationary distribution, which you get if you run policy pi in environment PT, and if you sample your actions from this policy pi, then this is the average reward that we get, right? At time t, the environment at time t using policy pi. And we are trying to maximize that at time t. So our target is changing with time because at each time instant, the environment PT is changing. Therefore, we are chasing a moving target, right? An example of this is the following. So this is essentially how the S&P 500 index performed for over 80 years. So over this very long period of time. Now notice that there are seasonal time variations in how the market performed, right? There are few months where it goes way up, while few months where it goes way down. So there is some variation in this. The environment is changing. On top of that, this is past information. Even if we know that the stock market has certain seasonality as months progress, when we try to invest, we will have to contend with the fact that we don't know how the market will perform tomorrow or next month, right? So the environment is changing, that much we know, but how it changes, that we don't know. So we have two challenges. Now, because the environment is changing, we need to explore more aggressively than we were doing in a stationary environment, because we need to somehow figure out that the environment has changed significantly or not. Also, once the environment has changed significantly, we will need to forget what we learned about the old environment and learn some new things about this changed environment, right? So
So I have a question.
Yes.
Yeah, sorry to interrupt, but
Yeah.
can we augment the state space so that we add the time dimension also, because time is discrete, and thereby we make the whole model stationary again.
So you add a time dimension. So this will probably work in things which have a very strict seasonal pattern. Like, for example, where you have so for example, shopping has certain seasonal patterns, but it will still not be able to capture everything which is like time varying. So for example, such a model won't be able to capture the crash of 2008 in the stock market, for example, because that was like once in an event which happened once in a generation or even more than that, right?
Yes, but I don't think because that data is so rare, I don't think any model can capture that. But yeah.
Right. So like so we are not going to compare against a static adversary in this setting. We are going to compare against a dynamic adversary. So like your point is well taken, but it would only work in a setting where like you have a set of distributions which is not changing. So from one time instant or from one epoch to the next, you might get a different distribution, but it only comes from a fixed set.
Yeah. Okay. Thanks.
Yeah, thanks. Okay, so then let's look at the algorithm we can use to maybe help in this situation. So it's a very basic algorithm. It's very simple design that we built on top of Natural Actor-Critic. So let's discuss it. So suppose we have a horizon of length t, and we divide it into n segments of equal length. In that case, we restart our algorithm at the beginning of each segment. So we want to ensure sufficient exploration. So at the beginning of each segment, we restart the algorithm. And within each segment, we essentially run Natural Actor-Critic. So this is what we do. For the first t over n time instance, we run a Natural Actor-Critic algorithm. Then at t over n, we restart the algorithm. For the next t over n time window, we again run the Natural Actor-Critic algorithm, restart again, and so on. Okay. So this looks like a very simple algorithm. And but it turns out even analyzing this turned out to be challenging enough. So just to put the entire pseudocode at once, so we have a restart-based algorithm. Within a segment, as I said, we would do exactly what Natural Actor-Critic does. We initialize with a uniform policy, 0 value function, and 0 average reward estimate. And then we unroll our trajectory. And we create estimates of average reward, critic, we update the actor policy, and so on. The only difference within each segment compared to what we did in the stationary setting was that now the reward function is changing over time, and the transition probabilities are also time varying. Okay. Otherwise, the algorithm looks very similar.
No, excuse me.
Yeah.
In the previous slide, you have mentioning about the total segments n, right?
Yeah.
Is this n fixed or will you change it?
Yeah, so that's a little foreshadowing. So eventually, for the sake of analysis, we will fix this time segment. And okay, so I'll say a little at this stage. So we have two algorithms, one which assumes some knowledge of how the environment is changing, and the other which doesn't. But these segments will be fixed. So if you are looking for a more adaptive algorithm, which adapts to when the environment changes and only then does the restarts, we don't have it yet.
Okay.
Yeah.
No. One more question I was thinking was that is there any effective segments in the given time length, and is it something? Do you? I mean, can you explain something about it? Can we find some effective number of segments that we need to?
So essentially, it depends on how rapidly your environment is changing, right? So when I show the eventual theoretical result, then we will see that if the environment is changing very rapidly, then we will need more restarts. Yeah.
Right. Okay.
Yeah. So we'll get to that. Yeah.
Okay.
Yeah.
I think I missed this, but what are we using fixed learning rate, or are we using some form of decaying learning rate?
Yeah. So like, just wait a few slides. We'll get to that. Yeah.
Pranay, is this does this have parallels with MPC?
MPC meaning? Sorry.
Model predictive control. So
sorry, like I don't know enough MPC. I'm sure there is, because like you see in papers the same terminology, but I don't know that literature, so I cannot give you a good answer.
All right. Okay.
Yeah. Okay, so now that we have an algorithm, let's see how it does. So let's look at the regret bounds. So what is our goal? We started with the objective that we want to maximize the time averaged reward in the long run. That was our average reward. And we modify it very slightly, and we use something called dynamic regret. And this is how we define it. So look at each time instant, look at the difference that we have. So we are subtracting the reward that our algorithm gets, right? And we are subtracting it from this quantity, JT pi t star. So at time t, what is the policy that achieves the maximum average reward? Okay, so in the environment that exists at time t, what would have been the policy that maximizes the average reward for this environment? Okay, that is pi t star. And we look at the average reward for this policy, and that is what we are comparing our actual reward against, right? So as I said, again here, we are chasing a time varying target because this JT pi t star would evolve over time, right? Another thing to note here is that compared to things like online learning, where we similarly have notions of dynamic regret, but the difference there is always positive. In this case, you might happen that your instantaneous reward might end up exceeding this JT pi t star because this is an average, right? But this is the definition which is like widely used in non-stationary RL setting. So we'll stick to this. And in the initial works, for example, this paper by Evandar et al., they considered static regret, where you compare the cumulative reward of a single stationary policy. What we are doing is much more general and much harder than static regret. Okay. And because we are going to look at dynamic regret, we need to quantify how the environment is changing. So which is done through variation budgets. And these are the cumulative changes in the reward vectors and the cumulative changes in the transition probabilities. So we have delta RT, which quantifies how much the reward vectors are changing from one time instant to the next cumulatively. And similarly, delta PT quantifies how much the transition probabilities are changing from one time instant to the next cumulatively. I think I missed a... Yeah, also, naturally, we don't assume that these the exact values of how much the reward function and transition probabilities have changed. This is assumed unknown. I'll talk about an algorithm where we assume knowledge of this delta t, but we also have an algorithm which doesn't need that knowledge. And we have made the following assumption of uniform ergodicity. So given policy pi in environment P, uniform ergodicity means the following, that there exists a constant m, which is positive, and a number rho, which is smaller than 1, such that starting in environment S, if you let your trajectory run, then at time tau, the distance of this distribution from the stationary distribution is going to fall exponentially fast. Okay, this distance is exponentially falling as you increase the time horizon. So we make a seemingly strong assumption that the Markov chains induced by all potential policies in all environments are going to be uniformly ergodic with certain m and rho. Okay. And under this strong assumption, we have the following regret bound. So given the knowledge of variation budget, we use the following step sizes. So these are the step sizes for tracking the average reward, the critic estimate of value function, and the actor's policy parameters. So this is the algorithm that we run on the right. This is a single segment of that algorithm. So if these are the parameters that we used, and these are the number of restarts that we do, in that case, this is the dynamic regret bound that we get. Okay. So I'll stop for any questions here.
Yeah, I have a question. Rather than restarting the value function to the value function we learned and the policy we learned, also we can just restart the step sizes only. How would that work?
What do you mean by restart the step sizes?
That is when you're going to so when we set t back to 1.
Right. Oh, wait.
Without yeah.
So here the step sizes are all constant. So I didn't get what you mean by.
Oh, okay.
Yeah.
Okay, then I have another question.
Yeah. Hello? Hello? Can anyone else hear me?
Yes, sir, you're audible.
Yes, you're audible.
Okay. Okay, I'll continue. I thought there was a question. Okay, so this is the dynamic regret bound. Yeah, like let me know if there are any other questions. So this is the dynamic regret bound that we get. Let me say a little more about this bound. So as I said, these are the values of the step sizes for average, reward, critic, and actor, and these are the number of restarts that we do. And clearly, if like this variation budget is going to capture how much non-stationarity is in our setting, or how much cumulatively the system is changing. So if the variation budget goes up, then naturally our average reward become worse. If it's linear, then we can't really do anything, which is again understandable. Also, if we have a rapidly changing environment, meaning we have a large variation budget, in that case, we must adapt quickly, which is shown by this delta t appearing in the numerator in all the step sizes. And we should restart more often because the environment is changing rapidly. So like the information that we have learned becomes stale more often. So we should restart more often. And naturally, since we are in a finite state, finite action setting, if the number of states is huge, the number of actions is huge, we will need more samples to learn a good enough policy. Okay, so next, I would very briefly go over a proof sketch of this dynamic regret bound, and then.
So I have a question, Pranay.
Yes.
So when you were exploring the possibilities, instead of restarting, did you think about something else? Like instead of a hard restart, if you can do a soft restart, or maybe retain some information, some weighted information, or something like that. Did that kind of thought came into your mind, and can you elaborate on that?
Yeah. So we analyzed a very simple setting, and even that turned out to be challenged. So like when I'll talk about the future work, all these are like the future problems we want to tackle. Also, I would say one thing that when I'll show the lower bound which exists for this problem, then I'll also maybe I'll point that out again. That so Professor Veeravalli visited from UIUC visited IIT Bombay a few months back, and I had a conversation with him about this thing. And his suggestion was that without actively looking for change, you can probably not beat the lower bound. So the value function based method which beats the lower bound doesn't do active exploration. But in our case, like perhaps we need active exploration, but that brings out additional challenges, which like are again future work that I have in mind. But for this work, we did the very simple setting. The algorithm looks simple and stupid, but yeah, it is like as a first algorithm, it was complicated enough.
Okay. Yeah.
Thanks. Okay, so I'll very briefly talk about a proof sketch. I have more slides, but I'll skip most of them. And then I'll talk about like what are the drawbacks of this result and what are potential ways to address at least some of them. I'll also talk about a lower bound that exists. Okay, so this is our dynamic regret. Once again, we are at every time instant comparing the reward that we actually get against this quantity, which is the average, the optimal average reward in the current environment. So given PTRT, what is the optimal average reward? Okay, so let's first split this into two terms. Okay, the first is the optimal reward versus the actual average reward that our current policy would achieve. Okay, so we simply add and subtract this quantity. Now, if you look at the first term, this is simply the difference between average reward, what is the optimal average reward at the current time instant versus what is the average reward that our policy would actually get. And this is the actual average reward versus the instantaneous reward. So we have split our dynamic regret into these two terms, and then we can bound both of these separately. So this I've already said, this I've already said. So now let's focus on I1, which is the optimal versus the actual average reward. And again, you can split it again into several terms. So I have written it more explicitly that if we divide our entire time horizon into multiple restarted segments, in that case, if we add and subtract few things, we get this double summation. And now let's look at what is it that we added and subtracted. So the current time instant t, I have relabeled them as in the nth segment, we are at the hth time instant. Okay, so that's why nh plus n capital H plus lowercase h. So we have the optimal average reward at this time instant. We compare it against the optimal average reward, but at the beginning of this segment. Okay, so this is just a difference of two optimal average rewards, but in two different environments. One is the current time instant, and the other is the beginning of this segment. Then we add the same thing, the optimal average reward at the beginning of this segment. And at the same time instant, the beginning of the segment, we are looking at how well our policy would do. Okay, so look at the policy at the current time instant. Okay, but play it in the environment that existed at the beginning of the window. So what is the difference between the consequent average reward in the environment at the beginning of the segment, but two different policies? And then because we are subtracting it here, we get it in addition. And this thing is now comparing the same policy, but in two different environments. Okay, so I understand this is like quite a mouthful, but essentially in the first term, we are comparing two optimal average rewards at two different environments. In the second term, we are in the same environment comparing two different policies. And in the third one, we are comparing the same policy, but in two different environments. Okay. Now it turns out the first one, because the policies are optimal, so this should depend on how much the environment has changed, right? What is the optimal average in one environment versus what is the optimal average reward in the other environment? So this has to depend on how much the environment has changed. The last one, again, the policy is same, it's our policy, but we are evaluating it under two separate environments. So again, this has to depend on how much the environment has changed. The second one is essentially how suboptimal our policy is in a certain environment. So we are playing this policy, this pi underscore nh plus h in this environment at time instant nh. So how suboptimal our policy is, this should depend on our algorithm. Okay. So this is the three-way split that we do. And n, of course, will balance the exploration for change versus learning a good policy. I will skip these things. Essentially, as I said, the first term should depend on how much the environment changes. The last term can also be crudely bounded in terms of how much the environment changes, as you can see here. And it turns out to be good enough. The fourth term, the suboptimality of our policy, requires a little more work because now the error due to critic will come in. So I'll skip all this. I can go over this in more detail if there are questions at the end, but I'll skip all this and go to this slide. So this is essentially a summary of the entire proof sketch. So as I said in the beginning, we would split our dynamic regret into two separate terms. One is what is the, at each time instant, how much is the optimal average reward better than the average reward of my current policy. And the second term is how is the actual average reward different from my instantaneous reward at this time instant. Okay, so these are I1 and I2. As I said, I1 can be bounded in terms of how much the environment changes, basically my variation budget, and what is the error in the critic. So how bad the critic is in actually giving me the accurate estimate of the Q value function. The error in the critic can in turn be bounded in terms of how much the environment changes, how much the policy changes, and what is the average in the average reward. Remember, critic depended on the average reward estimator, and there'll be some exponential decay due to uniform ergodicity. And finally, average reward can again be bounded in terms of how much the environment changes and how much the policy changes. Right? And finally, this I2, this can again be bounded in terms of change in the environment and uniform ergodicity. So this is essentially like, I'm sorry for doing this very quickly, but this is essentially a summary of the proof sketch. So like let me say a little more about the results and what do they imply, what are the limitations, what are some potential directions next. So this is the lower bound which exists from this paper from last year. So it says that given any learning algorithm, you can construct a non-stationary MDP such that the dynamic regret would be at least this much. So in terms of time horizon, they have 2/3. Recall that we had 5/6. Okay. Also, in terms of the dependence on the state action sets, we had 1/2, they have 1/3. Okay. So this is significantly better lower bound. Here, D is the diameter of the MDP. So what is the reason for the gap between what this lower bound shows versus what we get? So the problem is that the natural actor-critic analysis that we do, so we have essentially done natural actor-critic with restarts, right? Now, therefore, we have to rely on analysis of natural actor-critic method. And it turns out there is some slack in that analysis. So essentially, we are forced to use a single loop 2-time scale algorithm. Why is that? Single loop is understandable. If the environment is changing at each time instant, you can't really run a double loop algorithm. However, the 2-time scale algorithm, where we have separate time scales for the actor and the critic, this our hand is forced by our analysis and the terms that we get. It turns out that if you look at natural actor-critic for infinite horizon in a stationary setting, there is a better algorithm. So if you insist on running a 2-time scale algorithm, then this is the error that you have to incur cumulatively. However, I didn't cite it here, but there is an existing paper which is able to improve this from 3/4 to 2/3 using a single time scale method. Okay, but it's very difficult to apply that analysis in our setting in presence of non-stationarity. So that's the first challenge. I don't think that would bring down from 5/6 to 2/3, because there is another analytic challenge which comes in the proof, which I can talk about at the end if there is some interest. But yeah, so essentially there are two separate challenges. One is because of the 2-time scale analysis of natural actor-critic, which we are forced to do, that introduces certain problems. So even in the stationary setting, that leads to this kind of a bound, while we want 2/3 in the non-stationary setting. Even taking care of that problem, there is another analytic challenge, which is deep into the proof. So there are these two challenges. Potential next steps. So of course, matching the lower bound or improving on our bound of T to the 5/6, that's definitely something which actively thinking about. Also, the point which Vaibhav raised a few minutes back, like, can you actively look for change? Can you like be a little more, rather than completely being agnostic to how your environment is changing, can you be a little more active in your search for, or in your algorithm? So that's again. Also, like, so far, everything is in a constrained setting. Like, we only talked about regret, but in a lot of settings, we work in a constrained environment. So, for example, I talked about self-driving cars as one of the motivating applications. There, you want to do well in the long run, but there are also certain constraints that you want to satisfy. For example, not running over someone, or not crashing into something, or not running out of your battery in the middle of nowhere. So in that case, constraint violation also comes up. Also, in the non-stationary setting, we might need stronger notions of constraint violation. Just cumulative constraint violation might not be good enough. Sometimes, like, you need stronger notion, like every time constraint violation should be every time constraint satisfaction. Also, like, and this relates to the point I made in response to Vaibhav some time back. Like, we assume that the change in the environment or the reward function is very exogenous, right? In the sense that we don't know or don't care about where this change came from. But in a lot of settings, the change is endogenous, or it might even be caused by our actions. So examples of endogenous changes in the environment are self-driving cars, where how you drive results in what kind of observations you make, what kind of environments, what kind of road conditions you will encounter in the future. Also financial trading, like for these big like financial entities, the kind of decisions, the kind of investments they make have a huge impact on how the market responds. So the environment changes because of their actions. Also, there are endogenous reward changes. For example, in recommendation systems. For example, when YouTube or Instagram shows you some kind of posts or some kind of video or some kind of content for the first time, you might enjoy a lot because of novelty, and therefore the system gets a huge reward. But if it keeps showing you the same thing, then because of staleness, like the reward function, you get used to that content. So the reward function, the magnitude of rewards can go down, or it can even become useless to show certain kind of content. So again, this is endogenous rewards, reward changes in rewards caused by what actions the agent took. So we haven't studied any of this. We assume complete exogeneity. Also, like most importantly, like how do these methods actually perform in practice? Like there is this big gap between reinforcement learning, research and theory versus practice. So again, this is something very much that I think about. Just to summarize, so we studied model-free policy-based algorithms to maximize average reward in an infinite horizon setting. We started with a natural actor-critic algorithm and generalized it to the non-stationary setting. So essentially, we introduced restarts into the algorithm. Ours is the first dynamic regret bound in this specific problem setting, policy-based algorithm, infinite horizon, average reward setting. So ours is the first bound on dynamic regret. I don't think even static regret exists in this space, but like don't hold me accountable on that statement. As I said, there is a gap between the lower bound and the upper bound that we have, and that results partly because of the natural actor-critic analysis that we are using in our proof. However, like so far we assumed that we knew the variation budget. So it was present in our choice of step sizes for all the step sizes, as well as the number of restarts that we did. If our variation budget was larger, we had to do more restarts, we had to use larger step sizes. What if we don't know that? Now we have an adaptive algorithm, which doesn't need to know the variation budget. Also, what if you're interested in doing function approximations? So like eventual goal of this thing would be to apply this thing in practical settings where deep learning would be essential. So we have some results in the linear function approximation setting as well. So this is the link of the paper, and it has been accepted in TMLR. I don't know if it has already appeared or it should appear very soon. So in last 1 minute, I want to talk about CMInDS. So we have a few in-house faculty members, including Parth Pandit, Arjun Bhagoji, and Prateek Javanpuria. These are the things they work on. Parth got a very prestigious Schmidt Science Early Career Fellowship last year. This is like very exclusive. Only 15 people in the world got it. And other winners include people like Percy Liang from Stanford. We have 2 more people who are joining very soon. One is an oceanographer and another is a devices person. So we are growing as a truly interdisciplinary department. We have a lot of associate faculty members from 15 departments at IIT Bombay. We are actively hiring. We have a few offers made out and we are actively hiring. So yeah, please do consider us. If you're a student, again, please do consider us. We have several graduate students. This 100 plus is old, so we have a lot more now. Admissions happen in March, April. Also, we have a pre-doc program, which is quite exciting. If you are an undergrad or a recent graduate, I would highly encourage you to check this out. With that, yeah, thanks. Thank you so much for inviting me. Thank you so much for having me over. I would love to take any more questions.
Thank you, Professor, for accepting our request and delivering a very interesting talk. Are there more questions from the audience?
Yeah, I can go to this is my email address. If anyone wants to reach out, I would love to chat about this more.
So I have a couple of questions. So
yeah,
one is, when the delta t is very small, does the regret bound matches with the regret bound in the stationary setting?
Right. So in the stationary setting, let me go back to the. So when you say the stationary setting, so our regret bound matches the T3/4, which you get for natural actor-critic in the stationary setting, but that is for the 2 time scale setting. In the single time scale setting, there is a slightly better algorithm which achieves a T to the 2/3 that we don't match.
Okay. And one more question regarding, so if you take the simpler setting of multi-arm bandits,
yeah.
So has there been works on like non-stationary multi-arm bandits with these kind of algorithms that you have proposed?
So I don't know much about multi-arm bandits. I'm actually taking a course by JK this semester, but like, aren't there other algorithms? I'm sure there are like extensions of EXP3 or UCB based algorithms in the non-stationary setting. Like bandit seems to be a much better understood setting. Like in the small literature review sections I read in these papers, there seem to be fairly good algorithms even in the non-stationary setting. But like natural actor-critic, like these kind of algorithms make sense in a RL setting. Like bandits has much better studied and much relatively simpler, if I can use that word, algorithms.
Okay. Yeah. Okay. Thanks.
Yeah. Thanks, Babu.
Thank you again, Professor. Thank you everyone for attending. Have a
Thanks
great
everyone.
evening.
This was great. Thanks for the questions.